Laplace transform part 1. So in this video is going to be the introduction of the Laplace transform. So we have been discussing about system in the time domain. So all signals were represented as function of time. But sometimes it is much easier to analyze signals and system when they are represented in the frequency domain. So in this particular subject, we are going to stress on how to write signal as a function of frequency and look at how systems respond to input of different frequencies. So you're going to learn on how to switch between time domain to frequency domain representation or vice versa. And you are going to be able to determine which domain is best suited for a particular problem. So frequency is the number of cycles per second of a period signal. So here we declare that any function written in the form of k exponent st, where k and s are the general complex constant, which is characterized by the complex frequency. So s here is equal to alpha plus j omega. So why do you apply Laplace transform? So Laplace transform is the dual or complement of the time domain analysis. So in the time domain analysis, we break the input st into impulsive components and sum the system response to all these components. But in frequency domain analysis, we break the input into exponential components. So that's why you have exponent st. And you know that s is equal to alpha plus j omega. So Laplace transform is the tool to map signals and system behavior from the time domain into frequency domain. So if you see this figure over here, usually you deal with time domain. So you have an input signal st coming into a system. So that system is denoted by ht, and that will give you an output of yt. So in frequency domain analysis, when you have a signal in time domain, first you Laplace transform the signal. It will become xs, and then it will go into a system which is denoted by hs because it's frequency domain, and this will give you an output of ys. So if you want to have the output in time domain, just simply inverse Laplace transform it, and you will get yt. Exponential function of st. Okay, so you know that s is equal to alpha plus j omega. So therefore, exponent st is equal to exponent alpha plus j omega t. And that will give you exponent alpha t times exponent j omega t. And we also know that j omega t, exponent j omega t is equal to cos omega t plus j sine omega t. That's why you will have the final equation as this. Also, we know that if you have a conjugate of s, so that will give you alpha minus j omega. So your exponent of s conjugate t will give you exponent alpha t times cos omega t minus j sine omega t. If your alpha is equal to 0, then we will have a function of exponent j omega t only. which has a real frequency of omega, because you don't have the alpha. So therefore, the complex variable S is equal to alpha plus j omega is the complex frequency. So this graph is showing you the signal. How does the signal behave? So when you have your alpha is equal to 0, so this would be your signal. If your alpha is less than 0, meaning that your S is on the left of y-axis, so you have a decreasing signal. On the other hand, if you have alpha is more than 0, this means that your S is on the right of y-axis and your signal is actually increasing. The form exponent st are the eigenfunction of continuous time. So why complex exponential of the form est are indeed eigenfunction of continuous time system? So we have learned before on how to do convolution. So a continuous time convolution formula would give you yt is equal to the integration of h tau at t minus tau d tau from minus infinity to infinity. So what you have to do is that you have to substitute the st to become exponent st. So that's why you will have yt is equal to h tau exponent s t minus tau d tau. So move exponent st outside the integral, so you will have it here. And lastly, use the definition of a Laplace transform, and this will give you a final equation of yt is equal to hs exponent st. Generally, there are two types of Laplace transform. So you have one-sided and also two-sided. So for two-sided Laplace transform, the signal of st, the Laplace transform is defined by, so you have xs, because you have applied Laplace transform. So that is actually the multiplication of st times exponent minus st, and then integrate it from minus infinity to infinity. So the signal st is said to be the inverse Laplace transform of xs. So if you want to get back the st, you apply inverse Laplace transform. So you have st is equal to 1 over 2 pi j, and then integrate xs exponent st ds from c minus j infinity up until c plus j infinity. So c is actually a constant which is chosen to ensure that the convergence of the first integral. Okay, now the one-sided Laplace transform. So symbolically, it can be shown as xs is equal to L st, and st is actually the inverse Laplace transform of xs. So it is also a common practice to use a bidirectional arrow to indicate a Laplace transform pair. So you can also use these arrows to show that, okay, st Laplace transform to xs. So if all the signals are causal, its Laplace transform is defined by, so you will have xs is equal to the integration of st times exponent minus st dt from 0 up until infinity. So if the question asks you the difference between one-sided and two-sided, so you can use this information. So unilateral, which is one-sided, is used in the solution of differential equation with initial condition and analysis of causal. Okay. Causal LTI-CT system. Bilateral, on the other hand, is used in the steady state zero initial condition analysis of LTI-CT system, and it is for non-causal system. So definition of Laplace transform. So one-sided LT. So you have Laplace of ft would give you Fs. So it is being transformed from time domain into frequency domain. So you will have the integration of ft times exponent minus st dt. Integrate it from 0 to infinity. Okay, the principle of superposition holds in Laplace transform. So this is just showing you the linearity of the Laplace transform. So when you have two incoming signal, which is x1t and x2t, so when you apply Laplace transform to it, this will give you x1s plus x2s. And finding the inverse Laplace transform actually requires integration in the complex plane. So there are a lot of examples. So usually just use a Laplace transform table that will be given to you. So you can just refer to this table in order to get the answers. So how to use this table? So you have xt over here. So that would be in time domain, the input in time domain. And then xs is the input in frequency domain when you apply Laplace transform. So if you have an impulse of, an impulse in time domain, so when you apply Laplace transform, that will give you 1. So another example, if when you have a step function ut in time domain, apply Laplace transform, you will get 1 over s, which is in frequency domain. So please go through all these examples, the table of the Laplace transform, and please try out these examples as well. So here, determine the Laplace transform of each of the following functions. So the first one is asking you to apply Laplace transform to a step function, which is ut. So if I ask you to derive this equation, then you have to show me how to get it, or else you can just apply straight away from the table. So you have Laplace of ut. So apply the formula on how to get the frequency domain, and lastly you will get 1 over s, which is the same as shown in the table.